the in terms of actually, knowing when to stop and say, okay, when is this good enough? Well, there's a couple things to think about. First off, you could just keep on saying, all right, look, I mean, by eye you can tell certain things, right? And actually, it's normally better. I've always found that rather than just using a plain white piece of paper, if you use something like graph paper, where you have lines on it, that's going to give you a reference to kind of look at, and that's going to let you kind of look over a nice long distance and really be able to tell, because right now this beam might be slightly expanding or something like that. You might be able to do better. So it's worth it to kind of iterate through and just kind of look. So normally when I do this, I'll start by using some graph paper, and then just kind of looking over a nice long distance to be able to say whether or not it's good or not. Now, also, going further, what you can also do is you can use a beam profiler. So what you would do is you would send I don't think we need to go this far right now. With a beam profiler, what you would do is you'd make a series of measurements along the axis and say, okay, how big is the beam here at this point, at this point, at this point, and then you basically make a plot with the radius as a function of distance, and you can see whether the beam is diverging or contracting, and basically you can fit this to a Gaussian beam profile, of which the way you'd expect the light to propagate. We don't need to go so crazy, because also there's another complication to this, is that really, I talked about collimating the beam in terms of ray optics, right? But really the beams are Gaussian, so we can't use ray optics. We really need to use Gaussian beam propagation. So what Gaussian beam propagation tells you is that in order to describe a laser beam, I need to write down a waist and a waist position. So the waist is so normally when that's all right. There are formulas which tell you the way that this beam is going to propagate. It was something. So there's so what we define is that there's a position where the size of this beam is going to be the smallest, and that's what we call the waist. So if this is the smallest center line here, so this is normally called yeah, so this is like, imagine that my beam is propagating. So this is just actually the size of the beam. Okay. So I have my laser source over here, putting out the light, something like that, and it's going to do something like this. So it is. So there is a waist here, and all we need to do, we need to say what is the size of that waist, and what is and what's the position of that. And that tells us everything we need to know. Characterize the action. So the column. So this so because there is no collimated beam would really be this. It'd be two perpendicular, or parallel. But the thing is that with a Gaussian beam, that's impossible to achieve. So the best you can do is in a situation where you have there's some waist here, right, and you want to be in kind of this flat region of this. So it turns out that you can calculate for a given waist size, there's something called the Rayleigh range, which says basically the Rayleigh range is a characteristic height over which the waist will change for the. So normally we refer to two things. It's a little confusing. So specifically, the waist of the Gaussian beam is normally the size of the beam at its source. But then we also talk about a spot size, which is the spot size is whatever the radius of the beam is at a certain position. Okay. So I can write down that the spot size of the C is some function. Right? So what the Raleigh range tells us is basically it gives us a characteristic length over which the spot size increases from the waist size to like over 2 larger. So when you when you know, it's a good thing to know about this, look at the Gaussian optics and figure this stuff out, is that if you're trying to collimate your beam, right, you're saying, okay, I want to make this thing, I want to get to this situation. I'm never going to be able to do it. But you need to have a reasonable understanding of what is actually possible. Right? So because the best we can do is be somewhere in this region. And so if you calculate for about a given size beam, about what the radius of your beam is, you can calculate what the Raleigh range is. And it is, so for a large beam like that, it's actually going to be a pretty long. However, if you're ever working with a really small beam, something like